In this video, we'll introduce expanding binomials using Pascal's triangle. So before we introduce the idea of Pascal's triangle, we will first look at patterns in expanding binomials. So let's suppose we have a plus b to the power of 0, a plus b to the power of 1, a plus b to the power of 2 to the power of 3, 4, 5, and 6, and so forth. So let's expand these, and then let's see if we can find a pattern in expanding the binomials. So suppose we have a plus b to the power of 0. Well, that would just be 1. A plus b to the power of 1 is just a plus b. And a plus b to the power of 0 is 1 only if a plus b is non-zero. So then we have a plus b squared, and we already know how to square a binomial. It's a squared plus 2ab plus b squared. And then let's think about how we cube a plus b to the power of 3. Well, this would be equivalent to a plus b times a plus b squared. Okay, so this is equal to a plus b times a squared plus 2ab plus b squared. And now I can distribute a plus b into the brackets, so I would have that this is equal to a squared plus ab, because I'm going to distribute a plus b to each of these terms. I'm going to distribute a plus b to the first term, then to the second term, and then to the third term. So I would have a squared times a plus b plus 2ab times a plus b plus b squared times a plus b. And if I expand each of these, I get a cubed. Let me rewrite that here. So I would get a cubed plus a squared b plus 2a squared b plus 2ab squared plus ab squared plus b to the power of 3. So let's think about what that expands to, or what this simplifies to. Well, I've got a cubed. I've got that a squared b plus 2a squared b. Those are like terms, so I can combine them to get 3a squared b, because those are like terms. And then I've got, excuse me, I've got two other like terms. I've got 2ab squared and ab squared add together, or they combine to give me 3ab squared. And then my last term is plus b cubed. Okay, so we can use our knowledge of squaring a binomial and the distributive property to expand a plus b cubed. We can apply that to a plus b to the power of 4, but to save on time, I've already expanded a plus b to the power of 4 here for you. So a plus b to the power of 4, well, here I would just be distributing a plus b into a plus b cubed. And so I've already done this for you, but this expands to a plus b times a cubed plus 3a squared b plus 3ab squared plus b to the power of 3, which we got from this previous part here. So I just took ab cubed and I substituted that into here. So if you expand ab cubed, you get this. We already looked at that in the last example. And then you can distribute a plus b into the brackets to get this big long expression. When you combine like terms, you'll find that you get a to the power of 4 plus 4a cubed b plus 6a squared b squared plus 4ab to the power of 3 plus b to the power of 4. So let's see where that takes us. Well, now the next part of the question was to expand a plus b to the power of 5. And I would highly recommend you go through this as an exercise and you try it on your own. So if you want to pause the video and try that, I would strongly encourage that you do so. Let's go ahead and if we expand this, we know that a plus b to the power of 5, well, that should be a plus b times a plus b to the power of 4, which we already expanded. So we know that a plus b to the power of 4 is a to the power of 4, 4a cubed b, plus 6a squared b squared, plus 4ab cubed, plus b to the power of 4. So we're just going to multiply all of this by a plus b, and that'll give us a plus b to the power of 5. So just to save on time, I've already done this. And if we distribute a plus b into a plus b to the power of 4, we end up getting a to the power of 5 plus 5a to the power of 4b, etc. And then lastly, if we continue with this procedure, we get to expand a plus b to the power of 6. We would just get a to the power of 6 plus 6a to the power of 5b plus 15a to the power of 4b squared, etc. So let's think about this for a second. So it says in the question above, is there a pattern in the coefficients of terms? Is there a pattern in the coefficients of terms? So let's look for some patterns here in just the polynomials that we've expanded to. So notice that the first thing is that when we expand a plus b squared, notice that as we move from term to term, so for a plus b squared, there's 3 terms first off. Okay, so there's 3 terms for a plus b squared. We've got 1, 2, 3 terms. Another thing to notice is that the way that we've written this is descending in a, so that the first term is a to the power of 2, the second term is a to the power of 1, and the third term is a to the power of 0. We have this so that it's descending in b. So we have b to the power of 0, b to the power of 1, b to the power of 2. So with each successive term, the exponent of a decreases and the exponent of b increases. And it's the same thing with a plus b to the power of 3. When we expand a plus b cubed, we get a to the power of 3, a squared, a to the power of 1, a to the power of 0. And we have b to the power of 0, b to the power of 1, b to the power of 2, b to the power of 3. Let's see if that pattern continues when we expanded a plus b to the power of 4. It does. A to the power of 4, 3, 2, 1, 0. And then for b, we'd have b to the 0, 1, 2, 3, 4. The pattern also continues for a plus b to the power of 5. We have 5, 4, 3, 2, 1, 0. The exponents for b, we could write this as b to the power of 0, b to the 1, b to the 2, b to the 3, b to the 4, and then b to the 5. And same thing for a plus b to the power of 6. We have 6, 5, 4, 3, 2, 1, and 0 for the powers of a. For b, we have b to the 0, b to the 1, b to the 2, b to the 3, b to the 4, b to the 5, and b to the 6. So there's a definite pattern in the powers of a and b for each of the terms. But the question asks, what about the coefficients? So let's just start by writing out the coefficients. So when we expanded a plus b to the power of 0, we had coefficients of 1. Then we had coefficients of 1 and 1 for when we expanded a plus b. We had coefficient 1 and coefficient 1. When we expanded a plus b squared, we got 1, 2, 1. So let's go ahead and write that below. So this is 1, 1. And then we had 1, 2, 1. For a plus b cubed, we had 1. Let's see here. We had 1, 3, 3, 1. So let's write that below. 1, 3, 3, 1. For a plus b to the power of 4, let's see here. We had 1, 4, 6, 4, 1. So let's write that in this kind of triangular pattern that we have below. So we had 1, 4, 6, 4, 1. And then let's see, a plus b to the power of 5. We had, let us see here. We had 1, 5, 10, 10, 5, and 1. So let's write that in this pattern here. 1, 5, 10, 10, 5, and 1. And then a plus b to the power of 6, we had 1, 6, 15, 20, 15, 6, and 1. Okay, let's write this below. We had 1, 6, 15, 20, 15, 6, and 1. Okay, so let's see if we have discovered any patterns here now that we've gone through all this work of expanding all these binomials. And I know that was a lot of work, but sometimes it's worth it if you kind of figure out something useful from all that work. So one of the things to note is that all of the first coefficients are all 1. All of the last coefficients are all 1 as well. Okay, so that's something to note. Another thing to note is, let's see here. If I add these two values, I get 2. If I add these two values, I get 3. If I add these two values, I get 3. And let's see here. What if I add these two values? 1 and 3, I get 4. If I added 3 and 3, I would get 6. If I add 3 and 1, I would get 4. If I added 4 and 1, I would get 5. If I add 6 and 4, I get 10. If I add 6 and 4, I get 10. If I add 4 and 1, I get 5. If I add, let's see here, if I add 1 and 5, I get 6. If I add this term and this term, those coefficients, I get 15. And if I add these two coefficients, I get the coefficient in the next expansion. If I add 10 and 5, I get 15. And if I add, let's see here, if I add 5 and 1, I get 6. And so forth. So it certainly seems like there's a pattern, and this triangular pattern. It seems like if I added, let's see here. Let's continue this. Okay, let's put a 1 there and put a 1 there. And now if I add 1 and 6, I would get 7. Let's do this in a different color. If I added 1 and 6, I would get 7. If I added 6 and 15, I would get 21. And if I added 15 and 20, I would get 35. 20 and 15, I would get 35 as well. 15 and 6, I would get 21. And 6 and 1, I would get 7. So let's see, how many values do I have in this row? I would have, let's see here. I have 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 values in the row of this triangle, and I leave it up to you to try to expand a plus b to the power of 7. And do we get coefficients from the next row of this triangle? So that is is the coefficient of the first term 1, the coefficient of the second term 7, 21, 35, 35, 21, 7, and so forth. So try that out as an exercise and see if we can get the if we expand a plus b to the power of 7, does it give us the next row of this triangle?